For decades, we have been taught that the vacuum of space is a place of absolute silence. We imagine it as a void where no sound can travel and no vibration persists, a sterile emptiness stretching between the stars. That assumption was wrong. The space between our sun and the next star is not empty, nor is it silent. It is filled with an invisible, shimmering medium that vibrates with a persistent energy. Far beyond the reach of any human eye, a lone machine has discovered that the void actually hums. This is not the sound of wind or the echo of an explosion. It is a signal born from the interaction of charged particles, a cosmic frequency that tells us we have finally left the sanctuary of our own star. The scale of this discovery is immense. We are no longer talking about distances measured in miles or even millions of kilometers, but in astronomical units, where one unit equals the vast gap between the Earth and the Sun. To understand what Voyager 1 is hearing, we must first understand the fragility of its existence and the impossible distance it has traveled to reach this threshold. Launched on September 5th, 197th and 7, Voyager 1 was never intended to be a permanent resident of the interstellar void. It was built for a specific set of goals, designed as a scout to visit the giants of our outer solar system. When it first left the launch pad, its primary objective was to provide us with our first close-up looks at Jupiter and Saturn. At that time, the outer planets were mysteries wrapped in clouds of gas and ice. The spacecraft carried a suite of instruments meant to capture images and measure magnetic fields, all while operating on a power source that would slowly fade over decades. As it accelerated away from Earth, Voyager 1 began its long journey through the dark. It moved with a steady, unrelenting momentum, carving a path through the solar system that no other human-made object had ever dared to follow. The machine was a marvel of 70s engineering, a collection of gold-plated circuits and aluminum frames held together by the hope that it would survive the radiation belts of the gas giants. Every mile it traveled pushed it further from the warmth of the sun and deeper into the cold indifference of the deep. The encounters with Jupiter and Saturn were triumphs of precision. The spacecraft swung around these massive worlds, using their gravity to slingshot itself even further into the abyss. We saw the Great Red Spot in detail for the first time and witnessed the complex architecture of Saturn's rings. But as Voyager 1 moved past these landmarks, its mission shifted from exploration to endurance. It stopped being a photographer and started becoming a sentinel. The planets faded into distant points of light, and the spacecraft entered the long, slow drift toward the edge of everything we knew. To understand where Voyager 1 is now, we have to visualize the environment it has spent decades traversing. Most people think of the solar system as ending at Pluto, or perhaps the Kuiper Belt, but there is a much larger structure at play. Our sun does not just emit light and heat. It constantly breathes. It releases a powerful stream of charged particles known as the solar wind. This wind blows outward in every direction, creating a massive, invisible bubble that envelops everything from the inner planets to the furthest reaches of the outer system. This bubble is called the heliosphere. It is our cosmic shield, a protective cocoon that guards us from the harsh radiation of the galaxy. Inside this sphere, the rules are dictated by the sun. The plasma, a hot, ionized gas consisting of electrons and protons, flows outward at supersonic speeds, pushing back against the pressure of the interstellar medium. For billions of years, this bubble has been our only home, a pocket of solar influence in an ocean of galactic plasma. As Voyager 1 traveled further away, it began to feel the pressure of this boundary. The solar wind does not simply stop. It slows down as it encounters the resistance of the gas and dust that exists between the stars. This creates a region of turbulence known as the termination shock. It is a place where the fast-moving particles from our sun crash into the slower, denser material of the interstellar void. Imagine a river flowing into a vast, still lake. There is a point where the current breaks, creating ripples and eddies before the water settles. Voyager 1 spent years navigating this transition. The spacecraft was no longer just flying through space. It was fighting against the changing density of the plasma around it. The instruments on board began to register shifts in the environment that were subtle but profound. The magnetic fields grew more complex, and the flow of particles became erratic. The probe was moving through the heliosheath, the outer layer of our solar bubble, where the solar wind is compressed and heated. In this region, the spacecraft became a floating laboratory, measuring the invisible forces that define the border between our star and the rest of the Milky Way. The engineers on Earth, thousands of miles away in the control rooms of NASA, watched as the data trickled back across billions of kilometers. They were looking for a specific signature, a drop in solar particles and a rise in galactic cosmic rays. These cosmic rays are high-energy particles from distant supernovae that usually cannot penetrate the heliosphere. When they began to dominate the readings, it was a sign that the shield was thinning. The transition is not a sharp line like a wall, but a gradual fading of influence. It is a slow dissolution of the sun's grip on its surroundings. As Voyager 1 pushed deeper into the heliosheath, it entered a realm of profound isolation. The sunlight that reached its panels had become a dim glow, barely distinguishable from the background stars. The spacecraft was now operating in a state of extreme hibernation, with most of its systems powered down to conserve the dwindling energy of its radioisotope thermoelectric generators. These power sources are small pellets of plutonium that generate heat, which is then converted into electricity. Over time, this heat decays. Every single watt of power on Voyager 1 is precious. To keep the mission alive, NASA has had to make agonizing choices about which instruments to keep running and which to sacrifice forever. The spacecraft is a dying ember in the dark, yet it continues to speak to us, sending pulses of data that take nearly an entire day to reach Earth. The journey through the heliosheath was a lesson in patience. For years, Voyager 1 seemed to be hovering on the threshold, neither fully inside nor fully outside. The plasma density fluctuated, teasing the scientists with hints of the boundary before receding. It was as if the solar system were reluctant to let go of its furthest messenger. But the momentum of the launch in 1977 remained. The probe continued its outward trajectory, driven by a physics that does not care about time or distance. As we contemplate this journey, it is helpful to think about the sheer physical scale of the void. If you were to hold a single grain of sand between your finger and thumb, and imagine that grain represents our sun, the nearest star would be another grain of sand located 4 miles away. Voyager 1 is currently somewhere in the vast, empty stretch between those 2 grains. It has traveled further than any piece of human technology in history, crossing distances that defy our natural intuition. The space it occupies now is not a vacuum in the way we think of it on Earth. It is filled with the interstellar medium, a thin, ghostly soup of hydrogen and helium plasma. This plasma is the residue of ancient stars, the raw material from which new worlds are born. By entering this medium, Voyager 1 stopped being a planetary probe and became an interstellar explorer. It crossed the heliopause, the final boundary where the solar wind finally gives way to the pressure of the galaxy. This crossing was not marked by a flash of light or a sudden jolt. Instead, it was revealed through a series of anomalies in the data. The scientists noticed that the plasma density around the craft had suddenly jumped. It wasn't a gradual increase, it was a step function change. The environment had shifted fundamentally. The spacecraft was no longer swimming in the breath of the sun. It was drifting in the currents of the Milky Way. But there was a problem. One of Voyager 1's primary tools for measuring this transition, the plasma science instrument, had been damaged years earlier during the encounter with Saturn. It had been shut down long before the spacecraft reached the edge of the solar system. For a time, it seemed as though we would have to guess where the boundary was based on indirect evidence. We had the magnetic field data and the particle counts, but we lacked the direct measurement of the plasma density. This is where the mystery deepened. Despite the failure of the primary plasma instrument, another system began to register something strange. The plasma wave system, a different instrument designed to detect electric field fluctuations, started picking up oscillations. These were not random noises. They were structured waves that behaved like a bell being struck. When these waves occur, they create a frequency that is directly tied to the density of the surrounding plasma. The researchers discovered that by analyzing these oscillations, they could infer the density of the interstellar medium without needing the damaged plasma science instrument. The spacecraft was effectively using its own body as a sensor, feeling the vibrations of the void. These measurements provided the definitive proof that Voyager 1 had crossed into interstellar space. The density of the plasma outside the heliopause was significantly higher than what is found inside the solar bubble. This discovery changed our understanding of the local neighborhood. We realized that the heliosphere is not a perfect sphere, but a distorted shape, compressed by the interstellar wind. Voyager 1 had found its way through a gap in the armor, slipping out into the galactic sea. The data revealed that we are moving through a region of space that is more crowded with plasma than previously thought, suggesting that the pressure from the outside is stronger than our sun's ability to push back. The experience of Voyager 1 is one of profound loneliness. It is a small, metallic seed cast into an infinite field. As it drifts, it carries with it the only physical record of our existence that may survive for millions of years. The golden record, etched in gold-plated copper, contains sounds and images of Earth, the laughter of children, the songs of whales, the greetings of dozens of languages. It is a message in a bottle thrown into a cosmic ocean, though the chances of it ever being found are infinitesimally small. Yet, there is something deeply poetic about its current state. The probe is no longer looking back at the planets. It is focused entirely on the dark. Its instruments are tuned to the frequencies of the void. By listening to the plasma waves, Voyager 1 is acting as a surrogate ear for humanity. It allows us to hear the texture of the galaxy, to sense the ripples caused by solar disturbances that travel far beyond our home. When a solar flare erupts on the surface of the sun, it sends a shock wave of energy screaming outward through the solar system. These shocks eventually reach the heliopause, where they strike the interstellar plasma like a hammer hitting a drum. Voyager 1 detects these impacts as bursts of plasma waves. By timing these events and measuring their frequency, scientists can map the distance between the sun and the edge of its influence with incredible precision. This process transforms the void into a medium of communication. The hum that Voyager 1 detects is actually a series of responses to the sun's activity. It is a conversation between our star and the interstellar medium, and Voyager 1 is the only witness to this dialogue. Each oscillation provides a data point, a tiny piece of a puzzle that describes the boundary of our cosmic home. The frequency of these waves, often hovering around 2.6 kilohertz, is not something we can hear with our ears in the traditional sense. Space is a vacuum, and sound waves cannot travel through it. However, plasma waves are oscillations of electric fields and charged particles. When scientists convert this electrical data into audio frequencies, it sounds like a low, persistent hum or a whistling wind. This sonification allows us to perceive the density of space as a sound, turning abstract numbers into a visceral experience. The hum is not a constant tone. It shifts and wavers. It reflects the turbulence of the local interstellar medium. Just as a boat feels the chop of the ocean waves, Voyager 1 feels the compressive turbulence of the plasma outside our bubble. These fluctuations tell us that the space between stars is not a stagnant pond, but a dynamic environment filled with currents, pressures, and invisible storms. As we move further into this narrative, we must acknowledge the sheer fragility of the link between Earth and the probe. The Deep Space Network, a collection of massive radio antennas in California, Spain, and Australia, is the only thing keeping Voyager 1 connected to us. The signal it sends is unimaginably weak by the time it reaches our atmosphere. It is a whisper traveling across a distance that would take thousands of years to cross at the speed of a commercial jet. The power budget for this communication is now critical. Every single instrument that remains active consumes precious energy from the decaying plutonium cores. NASA engineers have become masters of efficiency, turning off heaters and non-essential sensors to ensure that the most important tools stay online. The goal is to keep the spacecraft breathing, to let it continue its measurements as long as physically possible. The current state of Voyager 1 is a testament to human curiosity. We sent a machine into the dark with no guarantee that it would survive more than a few years, and yet it has persisted for nearly half a century. It has outlived the careers of many of the people who built it. It has become a ghost ship, sailing through a sea of plasma, reporting back from a place where no other operating spacecraft has ever been. The data coming back now is different from the data of the 70s and 80s. We are no longer interested in the rings of Saturn or the moons of Jupiter. We are interested in the gradient, the way the density of space changes as we move further away from the Sun. The measurements suggest that there is a large-scale transition occurring over tens of astronomical units, a slow blending of solar and interstellar environments. This gradient is one of the most mysterious aspects of the voyage. It suggests that the boundary between our system and the galaxy is not a sharp line, but a complex zone of interaction. Voyager 1 is currently mapping this zone, providing the first in-situ measurements of how the plasma density evolves as we move deeper into the void. This information is crucial for understanding how our solar system interacts with the Milky Way, and how the interstellar medium protects us from high-energy radiation. As we drift along with the probe, we realize that Voyager 1 is more than just a piece of hardware. It is an extension of human consciousness. For the first time in history, we have a physical presence outside the heliosphere. We are no longer just observers looking through telescopes. We have a finger touching the interstellar plasma. The hum detected by the plasma wave system is the sound of that touch. The solitude of the spacecraft is absolute. There are no other ships nearby, no stations to dock with, and no landmarks to guide its way. It is moving at speeds of over 38,000 miles per hour. Yet in the scale of the galaxy, it is barely moving at all. It will take tens of thousands of years for Voyager 1 to come close to another star. Until then, it remains our furthest outpost, a lonely sentinel in the dark. The persistence of the signal is what makes this journey so haunting. Every time a packet of data arrives at the Deep Space Network, it is a victory over entropy. It is a confirmation that the machine is still there, still functioning, still listening to the vibrations of the void. The hum continues, a steady heartbeat in the silence of interstellar space, reminding us that even in the furthest reaches of the dark, there is something to be found. As we contemplate the distance, we can imagine the spacecraft as a tiny spark of light moving through an endless midnight. It carries our history and our hopes on a gold-plated disc. but its true legacy is the data it sends back. The measurement of plasma density, the detection of cosmic rays, and the recording of those strange oscillations are the real messages we are receiving. They tell us that we are part of a larger, vibrating universe, and that the void is not empty, but full of hidden energy. The transition from the solar wind to the interstellar medium is a metaphor for our own quest for knowledge. We start in the warmth and safety of what we know, the heliosphere of established science, and we push outward into the unknown. The process is slow, often confusing, and marked by periods of uncertainty. But eventually, we cross the threshold. We find that the assumptions we held were incomplete, and we discover a new reality waiting for us in the dark. Voyager 1 has taught us that the boundary of our solar system is not an end, but a beginning. It is the point where our local story merges with the galactic story. The hum it detects is the sound of that merger. It is the frequency of the interstellar medium, the baseline noise of the galaxy, and it serves as a reminder that we are never truly isolated from the rest of the cosmos. As the spacecraft continues its journey, it will eventually run out of power. One by one, its instruments will fall silent. The heaters will fail, and the electronics will freeze in the absolute cold of space. But even then, Voyager 1 will continue to drift. It will remain a physical monument to an era of exploration, a silent messenger carrying the voice of Earth into the deep. For now, however, it still speaks. It continues to sense the plasma waves and record the density of the void. Every oscillation is a piece of evidence, every frequency a clue to the nature of the interstellar medium. We listen to these signals with a mixture of awe and melancholy, knowing that we are hearing the final reports from the most distant scout humanity has ever sent. The scale of this operation is humbling. From the launch pad in Florida to the edges of the interstellar void, Voyager 1 has spanned the gap between our world and the galaxy. It has transformed the way we perceive our place in the universe, turning a theoretical boundary into a measured reality. The hum it hears is not just data. It is the sound of us reaching out and finally touching the infinite. To understand how Voyager 1 reached this state of isolation, we must first look at the architecture of our cosmic home. The sun does not simply shine, it breathes. It constantly exhales a stream of charged particles known as the solar wind, a torrent of plasma that pushes outward in every direction. This wind creates a massive, invisible bubble around everything in our solar system, a sanctuary called the heliosphere. For billions of miles, this bubble shields us from the harsh environment of deep space, acting as a magnetic umbrella that deflects the majority of high-energy cosmic rays coming from other stars. As Voyager 1 traveled away from the Sun, it was moving through this protective layer, sailing against the current of the solar wind. For decades, the probe experienced the gradual thinning of this plasma, a slow decline in pressure as it pushed further into the outer reaches of our stellar neighborhood. The journey toward the edge is not a smooth transition. Long before Voyager 1 reached the actual boundary of interstellar space, it encountered a region known as the termination shock. This is the point where the solar wind, which has been screaming outward at supersonic speeds, suddenly slams into the denser material of the local interstellar medium. It is a cosmic braking zone. Imagine a fast-moving river meeting a still lake. The water piles up and slows down, creating turbulence and pressure. At the termination shock, the solar wind drops to subsonic speeds, becoming denser and hotter as it compresses against the outer wall of the heliosphere. When Voyager 1 passed through this region, its instruments recorded a shift in the behavior of the particles around it. The spacecraft was no longer in the free-flowing stream of the sun's breath, but had entered the heliosheath, a transitional zone where the solar wind wanders and swirls before finally stopping. The heliosheath is a place of profound instability. It is here that the magnetic fields of our Sun clash with the magnetic fields of the galaxy. The probe spent years navigating this chaotic buffer, measuring how the plasma behaved as it was squeezed between two opposing forces. This region serves as the final frontier of solar influence, a thick skin that protects the inner planets from the raw radiation of the void. As Voyager 1 pushed deeper into the sheath, the data began to change in ways that challenged our existing models. The transition was not a simple line on a map, but a complex, undulating boundary that breathed and shifted based on the activity of the Sun. Eventually, the probe reached the heliopause. This is the ultimate edge, the point where the outward pressure of the solar wind exactly balances the inward pressure of the interstellar medium. Crossing the heliopause is like stepping out of a house into a storm. One moment, you are enveloped in the familiar plasma of your own star. The next, you are immersed in the plasma of other stars. In August 2012, Voyager 1 officially crossed this threshold at a distance of roughly 121 to 122 astronomical units from the Sun. To put that scale into perspective, 1 astronomical unit is the distance from the Earth to the Sun. Voyager was more than 100 times further away than we are, drifting in a region where the Sun is no longer the dominant force shaping the environment. The evidence for this crossing did not arrive as a single, dramatic event, but as a collection of subtle clues gathered by different instruments. The first sign was the behavior of cosmic rays. Inside the heliosphere, the solar wind blocks many of the high-energy particles originating from deep space. As Voyager 1 crossed the heliopause, the sensors recorded a sudden and sharp increase in these galactic cosmic rays, while the count of low-energy particles coming from the Sun plummeted. It was as if a curtain had been pulled back, exposing the probe to the raw, unfiltered radiation of the Milky Way. This shift provided the first strong indication that the spacecraft had left the solar bubble behind. However, the definitive proof required something more precise. Scientists needed to measure the plasma itself, the ionized gas that fills the void. This is where the story becomes a lesson in scientific resilience and improvisation. Voyager 1 was equipped with 2 instruments designed to study plasma: the Plasma Science Instrument and the Plasma Wave System. Unfortunately, the Plasma Science Instrument had been damaged during the spacecraft's encounter with Saturn decades earlier and had been shut down long before it reached the edge of the system. The team was left without their primary tool for measuring the density of the surrounding medium. They were sailing into the dark without a speedometer, unable to directly see the plasma that would prove they had entered interstellar space. But the plasma wave system remained active. While it was not designed to measure the density of plasma directly, it was designed to detect oscillations in the electric field, the waves that ripple through charged particles. In April 2013, the probe detected a series of plasma oscillations occurring near 2.6 kHz. These were not random noises. They were specific frequencies triggered by solar disturbances hitting the boundary from behind. By analyzing these oscillations, researchers were able to infer the local electron density of the environment surrounding the probe. The results were unmistakable. The density was significantly higher than what would be expected inside the heliosphere. It matched the predicted density of the local interstellar medium. This discovery turned a suspicion into a fact. Voyager 1 had not just wandered far, it had truly exited the solar bubble. How could a machine built in the 70s, with technology less powerful than a modern digital watch, provide such precise measurements from billions of miles away? The answer lies in the simplicity and robustness of its design. The plasma wave system continued to function because it was built to withstand the extremes of space, and because NASA engineers on Earth knew exactly how to interpret the subtle ripples in the data. The transition into interstellar space revealed that the void is far from empty. The plasma Voyager 1 encountered is a thin, ionized gas that permeates the galaxy, acting as the connective tissue between stars. By measuring this medium, the probe began to reveal the structure of our local neighborhood in the Milky Way. The data showed that there is a large-scale plasma density gradient across roughly 30 astronomical units of interstellar space. This means that as Voyager moves further away from the Sun, the density of the environment is slowly changing, suggesting that we are moving through a region of space with varying concentrations of matter. This gradient suggests that the heliopause is not a static wall, but a dynamic interface. It is a place where the solar system interacts with the galactic wind, creating ripples and folds in the plasma. The measurements also provided evidence of compressive turbulence outside the boundary. This turbulence indicates that the interstellar medium is stirred by distant supernovae, stellar winds from other stars, and the overall rotation of the galaxy. Voyager 1 is essentially feeling the weather of the Milky Way. It is detecting the invisible currents and pressures that shape the space between the stars, providing a tactile map of a region that no human will ever visit in person. The distinction between these measurements and actual sound is vital. In the vacuum of space, there is no air to carry acoustic waves. There is no wind to whistle through the antenna or thunder to roll across the hull. The hum we discuss is a translation. It is the process of sonification, where scientists take the electrical oscillations recorded by the plasma wave system and map them onto audio frequencies that the human ear can perceive. When we hear that low, persistent drone, we are not hearing the sound of space. We are hearing the density of the interstellar medium translated into a language we understand. It is a mathematical translation of the void's texture. This sonification does more than just make the data accessible. It reveals patterns that might be missed in a graph or a spreadsheet. The wavering quality of the hum reflects the turbulence of the plasma. A steady tone would suggest a perfectly uniform environment, but the fluctuations tell us that Voyager is moving through a medium filled with eddies and shocks. It is like listening to the difference between a still pond and a rushing river. By listening to the data, scientists can sense the chop of the interstellar ocean, gaining an intuitive understanding of the pressures acting on our solar system from the outside. As we dwell on these measurements, we must consider the sheer isolation of the probe. Voyager 1 is now so far away that it exists in a different temporal reality. A signal sent from Earth takes over 22 hours to reach the spacecraft, and another 22 hours for the response to return. Every command sent by NASA is a leap of faith, a message cast into the dark that will not be acknowledged for nearly 2 full days. This lag transforms the act of controlling the probe into a slow, meditative dialogue. The engineers are not operating a machine in real time. They are conversing with a ghost from the past, managing a vessel that is drifting further and further beyond our reach. The power remaining on board is the most critical constraint of this mission. Voyager 1 is powered by radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity. This heat is finite. As the plutonium decays, the available power drops every single year. To keep the plasma wave system and other essential instruments running, NASA has had to make agonizing choices. They have shut down heaters for non-essential components, allowing parts of the spacecraft to grow cold in a way that would be unthinkable for most missions. They have disabled cameras and sensors that no longer serve a purpose in the void. The mission has become an exercise in extreme conservation. Every watt of power, is precious. The goal is no longer to discover new planets or map moons, but to maintain the heartbeat of the probe for as long as possible. By stripping away everything unnecessary, NASA has extended the life of Voyager 1 well into the current decade. It is a skeletal version of the ship that launched in 1977, but it is a skeleton that still speaks. The fact that we can still receive data from an instrument designed before the invention of the personal computer is a miracle of engineering and persistence. The plasma wave measurements continue to be one of the most valuable streams of information coming back to Earth. Because these waves are triggered by solar events, they allow us to monitor the sun's influence on the interstellar medium in real time, or as close to real time as a 44-hour round trip allows. When the sun erupts, sending a shock wave through the heliosphere, Voyager 1 feels it. The resulting plasma oscillations tell us how that energy is dissipated at the edge of our system. This helps scientists understand not only the nature of the void, but also the protective capabilities of our own solar bubble. We are learning that the heliopause acts as a filter. It keeps out the most dangerous cosmic rays while allowing some to leak through, creating a complex radiation environment. By comparing the data from Voyager 1 with observations from Earth-based telescopes, we can see how the local interstellar cloud, the specific region of space our solar system is currently moving through, differs from other parts of the galaxy. We are discovering that our corner of the Milky Way has its own unique characteristics, its own specific density and temperature, which in turn affects how our solar system evolves over millions of years. The probe's journey also highlights the fragility of our understanding. For a long time, we assumed the transition to interstellar space would be abrupt, a clear line where one environment ended and another began. Voyager 1 showed us that this is not the case. The boundary is messy. It is a zone of interaction, a place where solar plasma and interstellar plasma mingle and fight for dominance. This realization has forced astronomers to rewrite their models of the heliosphere, replacing simple spheres with complex, distorted shapes that reflect the pressure of the galactic wind. As Voyager 1 drifts deeper into this medium, it continues to encounter regions of varying density. These changes are subtle, but they are significant. They suggest that the interstellar medium is structured in clouds and filaments, with some areas being denser than others. Voyager is essentially a needle threading through these cosmic fabrics, recording the change in texture as it goes. Each single data point is a victory over the immense distance and the decaying power of the craft. The solitude of this journey is perhaps its most defining characteristic. While other probes have explored Mars, Jupiter, or the asteroid belt, Voyager 1 is the only human-made object to have truly left the neighborhood. It has passed the point where it can be considered a part of our local system in any physical sense. It is now a citizen of the galaxy. The hum it records is the only sound it knows, the vibration of ionized gas and the distant echoes of our sun's activity. There is a profound poetic symmetry in the way Voyager 1 operates. It was launched to explore the giants of our system, but its greatest contribution has come from exploring nothingness. By measuring the vacuum, by listening to the plasma, it has defined the limits of our world. It has shown us where we end and where the rest of the universe begins. The data is a map of the invisible, a guide to the pressures and fields that govern the space between stars. The engineers at the Deep Space Network treat every signal with a reverence usually reserved for ancient artifacts. When a packet of data arrives, it is processed with extreme care, as if any loss of information would be an irreparable tragedy. They are listening to a whisper from 20 billion miles away, a fragile thread of radio waves that has traveled through the void to tell us that the machine is still alive. This connection is the only thing tying Voyager 1 to its creators. Without it, the probe would simply be a piece of drifting metal, an anonymous relic in the dark. But as long as the power lasts, the plasma wave system will continue to vibrate. It will continue to sense the electron density and the compressive turbulence of the interstellar medium. It will continue to report on the gradient of the void, providing us with a continuous stream of evidence about our place in the cosmos. We are no longer guessing what lies beyond the heliopause. We have a witness. The journey of Voyager 1 is a reminder that exploration is not always about finding something new to look at. Sometimes it is about measuring the things that cannot be seen. The hum of the plasma is an invisible phenomenon, yet it tells us more about the structure of our galaxy than 1,000 photographs ever could. It reveals the hidden architecture of space, the magnetic scaffolding, and the gas clouds that fill the gaps between the stars. As we move further into the silence, we realize that Voyager 1 has become a bridge. It connects the familiar warmth of our sun to the cold indifference of the interstellar void. It is a physical link between the known and the unknown. The data it sends back is not just science. It is a chronicle of departure. It is the story of a species that decided to reach out and touch the edge of its world, and then kept going. The plasma waves are the heartbeat of this journey. They are the only thing that changes in an environment of absolute stillness. By tracking these oscillations, we can feel the pulse of the galaxy. We can sense the movements of distant stars and the remnants of ancient explosions, all filtered through the sensors of a small, gold-plated probe. The hum is the sound of curiosity persisting against all odds, a steady signal in an ocean of silence. Every measurement of electron density, every detection of a plasma wave, adds another layer to our understanding of the interstellar medium. We are learning that the space between stars is not a void, but a reservoir of information. It holds the history of the galaxy's evolution and the secrets of how stars are born and die. Voyager 1 is providing the first in situ data for this study, turning the theoretical into the empirical. The scale of the distance now separating us from the probe is almost impossible to comprehend. If the Earth were a grain of sand, Voyager 1 would be miles away, drifting through a darkness that stretches for light years in every direction. Yet, despite this distance, we can still hear it. We can still feel the vibrations of the plasma it encounters. This connection is a testament to the power of human ingenuity and our refusal to accept the limits of our horizon. As the probe continues its trajectory, it will encounter more gradients and more turbulence. It will sail through different clouds of interstellar gas, each with its own density and its own unique hum. Each new region will provide a new piece of the puzzle, helping us understand the local bubble we inhabit and the larger galactic environment that surrounds us. The mission has evolved from a planetary tour into a galactic survey, one data point at a time. The persistence of Voyager 1 is an inspiration. It reminds us that the most valuable discoveries often come not from the loudest events, but from the quietest observations. The hum of the plasma is faint, nearly undetectable, yet it has redefined our understanding of the solar system's edge. It teaches us to listen closely to the silence, for in that silence, there are frequencies that tell the story of the universe. We must also acknowledge the human element behind this data. The scientists who analyze these signals are often working with instruments they did not build and theories that have evolved since their childhood. They are interpreting the whispers of a machine that was designed for a different era. This continuity of effort across generations of researchers is what allows Voyager 1 to remain relevant. The probe provides the data, but it is human curiosity that gives that data meaning. The plasma waves are more than just numbers on a screen. They are a sensory extension of our species. For a brief moment in cosmic time, we have an ear in the interstellar void. We can feel the pressure of the galaxy and hear the vibrations of the medium that separates us from our nearest neighbors. This experience is unique in human history. No other probe has gone this far and remained functional enough to speak back to us. As Voyager 1 moves deeper into the dark, it carries with it the weight of our collective ambition. It is a messenger that does not know its destination, only its direction. It is moving away from everything it ever knew, the warmth of the sun, the gravity of the planets, and the voices of its creators, to find something that has never been measured before. The hum it detects is the soundtrack to this ultimate departure. The transition from the heliopause into the interstellar medium was not just a scientific milestone, it was a psychological one. It marked the moment we truly stepped outside our home. We are now explorers of the deep, navigating a sea of plasma that extends far beyond the reach of any telescope. The data coming back is the only light we have in this region, a flickering signal that guides us through the unknown. The compressive turbulence Voyager 1 records is a reminder that the universe is always in motion. Nothing is truly still. Even in the deepest reaches of space, there are currents and waves, pressures and releases. The void is alive with energy, and Voyager 1 is our only way to feel it. The hum is the voice of that energy, translated into a frequency we can understand. As we reflect on the journey so far, we see that Voyager 1 has fulfilled its mission in ways its creators could never have imagined. It was sent to look at planets, but it ended up looking at the void. It was designed to take pictures, but it ended up listening to plasma. In doing so, it has provided us with a perspective that is entirely new. A view of our solar system from the outside looking in. The gradient of plasma density continues to be one of the most intriguing findings. It suggests that the interstellar medium is far more complex than we once thought. We are not just moving through a uniform gas, but through a structured environment with its own geography and weather. Voyager 1 is mapping this invisible landscape, providing the first physical evidence of the structures that exist between the stars. The communication link remains the most fragile part of the equation. Every time the Deep Space Network locks onto Voyager's signal, it is a triumph of precision. The antennas must be pointed with absolute accuracy to catch a signal that has been stretched and weakened by billions of miles of travel. It is a delicate operation, conducted in the quiet of the night across 3 continents, all to hear the hum of a lonely machine. The power budget continues to shrink, but the value of the data only grows. Each single measurement from the plasma wave system is now more precious than it was decades ago. We are racing against time, trying to gather as much information as possible before the plutonium cores finally fade and the spacecraft falls silent forever. This urgency adds a layer of poignancy to every signal we receive. The hum of the void is not just a scientific curiosity. It is a reminder of our own smallness. In the face of the interstellar medium, our entire solar system is but a tiny bubble, a fragile sanctuary in a vast and turbulent galaxy. Voyager 1 has shown us the scale of this contrast, mapping the boundary where our local influence ends and the galactic reality begins. As we drift along with the probe, imagining it as a silver needle in an endless midnight, we realize that its journey is a mirror of our own quest for knowledge. We push outward, we encounter boundaries, and we find that those boundaries are not walls, but gateways to deeper mysteries. Voyager 1 has crossed the final gateway, and it is telling us that there is so much more to discover in the dark. The plasma oscillations at 2.6 kHz remain one of the most iconic pieces of data from this mission. They were the key that unlocked the door to interstellar space, providing the definitive proof that Voyager had left the heliopause. That specific frequency became a landmark in the history of science, a sonic signature of our first true step into the galaxy. Even as other instruments are powered down, the plasma wave system remains a priority. Its ability to sense the environment without needing a direct sample of particles makes it an invaluable tool for studying the interstellar medium. It is the probe's most sensitive organ, its primary way of feeling the void around it. As long as this instrument lives, Voyager 1 is still exploring. The journey from the termination shock to the heliopause and finally into the interstellar medium has been a lesson in patience. It took decades for Voyager 1 to reach these boundaries, and years more to confirm exactly where they were. This slow-motion discovery reflects the true nature of space exploration, a process of gradual revelation, where truth emerges from the noise over long periods of time. The hum we hear is the sound of that patience. It is the sound of a machine that has waited for 40 years to tell us what it feels like to be outside our solar system. It is a voice that speaks in frequencies and densities, telling us that the void is not empty, but filled with the invisible breath of the galaxy. As Voyager 1 continues its flight, it will eventually move beyond the reach of even the deep space network. There will come a day when the signal becomes too weak to detect, or the power simply vanishes. On that day, the hum will stop for us, but it will continue for the probe. It will keep sailing through the plasma waves and the compressive turbulence, a silent witness to the secrets of the interstellar medium. But for now, the link holds. The signal arrives, the data is processed, and we are reminded that we have a scout in the dark. We can still listen to the vibrations of the void and wonder what else is waiting out there, beyond the gradient, beyond the turbulence, in the deep silence of the Milky Way. The measurements of the interstellar plasma provide a baseline for every other mission that will ever leave our system. Any future probe sent to another star will rely on the data Voyager 1 gathered during its first few years in the void. We are building our map of the galaxy on the foundation of these plasma waves, using the hum as a guide to the densities and pressures we will one day encounter again. The solitude of the spacecraft is not a tragedy, but a triumph. It is the loneliness of a pioneer. By being the only object in its environment, Voyager 1 provides a clean signal, free from the interference of other human technology. It is a pure observation, a direct interaction between a human tool and the raw materials of the universe. The hum of the interstellar medium is the final song of our first great voyage. It is a melody composed of ionized gas and magnetic fields, played on an instrument made of gold and aluminum. As we listen to it, we are not just studying physics, we are experiencing the feeling of departure. We are learning what it means to truly leave home. The plasma waves that Voyager 1 detects are not random noise, but reactions to specific events occurring millions of miles away. When a solar disturbance ripples outward from our sun, it travels through the heliosphere like a wave in a pond, eventually reaching the boundary where the solar wind meets the interstellar medium. These disturbances stimulate oscillations in the plasma, creating a rhythmic signature that Voyager's instruments can capture. It is as if the spacecraft is feeling the heartbeat of the sun, even though it has long since left the neighborhood. This interaction allows us to see how our star influences its surroundings far beyond the orbits of the planets, revealing that the solar system's reach is more dynamic and interactive than a simple static bubble. The plasma wave system operates by measuring these electric field fluctuations, translating them into data that describes the environment surrounding the probe. When the frequency of these oscillations hits approximately 2.6 kilohertz, it provides a critical piece of information: the local electron density. In the world of plasma physics, frequency is directly tied to density. By tracking this specific pitch, researchers can determine exactly how much ionized gas exists in a given volume of space. This measurement was the definitive proof that Voyager 1 had crossed into interstellar space. The density of electrons outside the heliopause is significantly higher than it is inside. And when the instrument recorded that jump in frequency, the team on Earth knew the probe had finally stepped through the door. This discovery changed our understanding of the local interstellar medium from a theoretical model to a measured reality. For years, scientists had hypothesized about the density of the gas between stars, but they were working with indirect evidence and distant observations. Voyager 1 provided the first in situ measurement, a physical touchstone that confirmed the environment was denser than previously expected. This means the interstellar medium is not a vacuum in the way we typically imagine it, but a thin ionized soup that exerts its own pressure on everything passing through it. The probe is essentially swimming through this medium, and the resistance it feels is what creates the data we call the hum. The persistent narrowband emission detected by the plasma wave system suggests that the interstellar medium possesses an inherent energy. This is not just a reaction to solar flares, but a constant, low-level vibration that exists independently of our Sun. It implies that the space between stars is filled with a background of plasma waves, perhaps generated by galactic supernovae, or the movement of magnetic fields on a scale we cannot fully conceive. By documenting this emission, Voyager 1 has revealed a subtle texture to the void. The darkness is not empty. It is humming with a quiet, persistent energy that permeates the galaxy. As the probe continues its trajectory, these measurements have allowed scientists to map a large-scale plasma density gradient over a distance of roughly 30 astronomical units. This is not a sudden wall, but a gradual slope, where the density of the interstellar medium shifts as Voyager moves deeper into the void. Mapping this gradient is like charting the depth of an ocean for the first time. It tells us that we are moving through different regions of the local cloud, each with its own characteristics and pressures. The fact that the density changes suggests that the interstellar medium is structured, potentially influenced by the movement of our entire solar system through the galactic arm. This gradient reveals a complex interplay between the heliosphere and the surrounding galaxy. We often think of the heliopause as a hard border, but Voyager's data shows it to be a transition zone. The way the plasma density shifts indicates that there is a blending of materials, a place where the solar wind and the interstellar wind negotiate their boundaries. This region is characterized by compressive turbulence, where waves of plasma crash into one another, creating pockets of high and low pressure. Voyager 1 is our only witness to this turbulence, recording the chaotic motions of gas that has never known the touch of our Sun. The nature of this turbulence provides a window into the physics of the deep void. Compressive turbulence means that the plasma is being squeezed and expanded as it moves, creating fluctuations in density that the plasma wave system can detect. This suggests that the interstellar medium is not a calm, stagnant sea, but a turbulent one, filled with currents and eddies on a cosmic scale. These movements may be driven by the magnetic fields of the galaxy itself, acting as invisible rivers that guide the flow of ionized gas. Voyager 1 is effectively drifting through these galactic currents, measuring the ripples they leave behind. To understand this data, we must distinguish between what we hear and what the probe actually senses. The hum is a sonification, a process where scientists take frequency data and map it to audible sound so that the human ear can perceive patterns that would be invisible in a spreadsheet of numbers. In the vacuum of space, there is no air to carry sound waves, so Voyager 1 does not hear a noise in the traditional sense. Instead, it detects oscillations in an electric field. When we listen to the hum, we are listening to the translation of plasma density into pitch. The sound is a mathematical representation of the void's physical state. This distinction makes the data even more extraordinary. we are not hearing a sound. We are hearing the architecture of space itself. The frequency of 2.6 kilohertz is a signature of the electron density, a numeric code that tells us exactly where the probe is and what it is touching. When researchers hear a shift in the pitch, they are witnessing a change in the physical composition of the galaxy. The sonification allows the human brain to detect anomalies and patterns in the plasma waves that might be missed in a visual graph, turning the scientist into a listener of the cosmos. The ability to use the plasma wave system in this way is a testament to the resilience of 1970s engineering. The probe's original plasma science instrument was damaged during its encounter with Saturn and was shut down long before it ever reached the edge of the solar system. For a time, it seemed that Voyager would be blind to the plasma density as it crossed the heliopause. However, researchers discovered they could use the plasma wave system, an instrument designed to measure waves, not particles, to infer the density by observing how the plasma responded to solar disturbances. It was an act of scientific improvisation, turning a secondary tool into a primary sensor. This pivot in strategy highlights the relationship between the mission team and the spacecraft. The scientists on Earth have had to learn how to read Voyager's instruments in ways that were never intended during the original design phase. They are treating the probe not as a static tool, but as an evolving organism. By finding new ways to interpret the data from the plasma wave system, they have extended the scientific life of the mission far beyond its original mandate. Every single bit of data recovered is a result of this creative persistence, a refusal to let the distance silence the machine. The plasma waves also tell us about the magnetic environment of interstellar space. Since plasma consists of charged particles, its movement is inextricably linked to magnetic fields. The oscillations Voyager records are essentially vibrations in these fields. By studying the hum, we can infer the strength and orientation of the galactic magnetic field as it interacts with the bubble of our solar system. This provides crucial data on how cosmic rays, high-energy particles from distant stars, are filtered or blocked by the heliopause. The hum is therefore a shield report, telling us how well our solar bubble protects the inner planets from the harsh radiation of the deep galaxy. As Voyager 1 moves further along its path, it continues to sample the local interstellar medium, providing a continuous stream of data that reveals the scale of the void. The 30 astronomical units of space sampled so far are just a tiny fraction of the distance to the nearest star. Yet they have already overturned several assumptions about the uniformity of the medium. We now know that the space between stars is characterized by fluctuations and gradients, meaning that any future interstellar mission must be prepared for a dynamic environment rather than a void of nothingness. The data coming back from the plasma wave system is processed through the Deep Space Network, a global array of giant radio antennas. Because Voyager 1 is so distant, the signal it sends takes nearly an entire day to reach Earth. When we hear a change in the plasma hum, we are hearing something that happened 22 hours ago. This time delay creates a strange, ghostly connection between us and the probe. We are listening to the past, receiving reports from a region of space that is already evolving by the time the data reaches our screens. This lag emphasizes the isolation of Voyager 1. It is operating in an environment where no other human-made object has ever been. While other probes have explored the planets and asteroids of our system, Voyager 1 is the only one that knows the true texture of the interstellar medium. Every oscillation it records is a first. The plasma waves are the only physical evidence we have of what lies beyond the heliopause, making the plasma wave system the most important sensory organ in human history. The compressive turbulence recorded by the probe suggests that the boundary between our sun's influence and the galaxy is not a clean break, but a messy, churning frontier. This region is where the solar wind slows down and piles up, creating a wall of plasma that Voyager had to push through. The hum changes as the probe moves from this wall into the open interstellar space, shifting from the chaotic noise of the boundary to the more persistent, narrow-band emissions of the void. This transition is the sonic map of our departure from home. As we analyze these waves, we are forced to confront the scale of the interstellar medium. The gradient in plasma density suggests that Voyager 1 is moving through a specific cloud of gas within the Milky Way. We do not know the boundaries of this cloud or what lies beyond it, but the hum provides the first clues. If the density shifts again in another few thousand astronomical units, it could indicate that we are entering a different region of the galaxy entirely, with its own unique chemical and magnetic properties. The persistence of these plasma waves indicates that the energy of the galaxy is omnipresent. There is no place in the void that is truly dead or silent. The hum is evidence of a universe that is constantly vibrating, shifting, and flowing. Even in the deepest darkness, there are waves of energy moving through the ionized gas, carrying information about distant stars and galactic events. Voyager 1 has become a tuning fork for the galaxy, vibrating in sympathy with the medium it traverses. This interaction between the probe and the plasma is a reminder of the physical reality of space. We often visualize the void as a black canvas, but for Voyager 1, space is a tangible substance. It is a sea of electrons and ions that creates drag, pressure, and vibration. The hum is the sound of this friction, the audible evidence that the spacecraft is not just floating in nothingness, but is moving through a physical environment with its own laws and rhythms. The researchers monitoring these signals often describe the process as an act of translation. They are taking raw voltage fluctuations from a 1970s sensor and turning them into a map of the galaxy. This requires a deep understanding of plasma physics and a willingness to embrace the unknown. When the plasma wave system detects a sudden spike in activity, it triggers a flurry of analysis on Earth as the team tries to determine if they have encountered a new structure in the interstellar medium or a temporary solar disturbance. These moments of discovery are often quiet. There are no flashing lights or sirens. There is only a line on a graph that moves slightly differently than expected. But for the scientists, these deviations are everything. They represent the first time any human instrument has ever encountered a specific phenomenon in interstellar space. The hum is the medium through which these discoveries arrive, a continuous stream of information that slowly fills in the blanks of our cosmic map. The relationship between the plasma density and the frequency of the waves allows us to calculate the pressure of the interstellar medium. This pressure is what shapes the heliosphere. By knowing exactly how dense the plasma is outside the bubble, scientists can work backward to understand why the solar system's boundary is shaped the way it is. Voyager 1 is essentially measuring the external pressure on our home, telling us how much the galaxy is pushing back against the wind of our sun. This balance of pressures defines the limits of our protective cocoon. If the interstellar plasma were denser or more turbulent, the heliopause would be smaller, and more cosmic rays would reach the inner solar system. Voyager's measurements are not just about the void, they are about the safety of our own world. The hum tells us how well we are shielded from the radiation of the deep galaxy, providing a scientific context for the fragility of our solar sanctuary. As Voyager 1 continues to drift, it serves as a benchmark for all future exploration. Any probe designed to reach another star will have to navigate the same plasma gradients and compressive turbulence that Voyager is recording now. The hum is the first set of navigational charts for an interstellar voyage. We are learning where the currents are strong, where the density shifts, and how the galactic magnetic field behaves. The data gathered by the plasma wave system is the foundation upon which all future deep space navigation will be built. The loneliness of the probe is amplified by the nature of its discoveries. It is detecting things that no other instrument can see because it is the only thing far enough away to feel them. The hum is a solitary song, sung by a machine that has outlived its creator's original expectations. It continues to function not because it was designed for eternity, but because it was built with a level of redundancy and simplicity that allows it to endure the harshness of the void. The plasma waves also provide insights into the composition of the local interstellar medium. While the plasma wave system measures density through frequency, these measurements can be compared with other data to infer what the gas is made of and how it is ionized. This helps astronomers understand the history of our local neighborhood in the galaxy. Whether we are moving through a remnant of an ancient supernova or a standard cloud of interstellar hydrogen, every shift in the hum is a clue to this history. A sudden increase in plasma density might indicate that Voyager has entered a denser filament of gas, while a decrease suggests a more vacant region of the void. By tracking these changes over decades, we are creating a long-term profile of the space between stars. We are discovering that the interstellar medium is not a uniform fog, but a complex landscape of peaks and valleys, currents and voids. The compressive turbulence detected by Voyager 1 is particularly fascinating because it suggests that the interstellar medium can support shock waves. These shocks can accelerate particles to incredible speeds, contributing to the flux of cosmic rays that bathe our galaxy. By measuring these waves in situ, Voyager is giving us a front-row seat to the engines of galactic acceleration. We are seeing how energy is transferred from large-scale magnetic movements down to the level of individual electrons. This process of energy transfer is what keeps the interstellar medium alive. The hum is the audible manifestation of this energy cascade. It tells us that the void is a place of constant activity, where plasma is being compressed and expanded in a never-ending cycle of galactic weather. Voyager 1 is our only meteorological station in this environment, reporting back on the winds and storms of the interstellar sea. The data from the plasma wave system also helps refine our models of how stars form and evolve. Since most stars are born from the collapse of interstellar clouds, understanding the density and turbulence of the medium is key to understanding the birth of suns. Voyager 1 is sampling the raw material from which future solar systems will be made. The hum it detects today is a preview of the conditions that existed billions of years ago when our own sun was forming from a similar cloud of plasma. This connection between the smallest electron oscillation and the largest galactic structure is what makes the mission so profound. A single frequency, 2.6 kilohertz, can tell us about the boundary of our solar system, the nature of the galaxy, and the origins of stars. The simplicity of the measurement belies the complexity of its implications. Voyager 1 has turned a simple piece of electronics into a window onto the fundamental physics of the universe. As we contemplate the probe's journey, we realize that the hum is also a measure of time. Each oscillation is a heartbeat, marking the seconds as Voyager moves further from everything it ever knew. The data arrives in bursts, separated by long periods of silence and processing. This rhythmic exchange of information, the probe sensing a wave, transmitting the data, and humans interpreting the sound, is a slow-motion conversation across the abyss. The persistence of the narrowband emission suggests that there are processes at work in the interstellar medium that we still do not fully understand. While we can measure the density and the frequency, the exact source of some of these plasma waves remains a subject of scientific debate. This is where the hum becomes truly mysterious. It is not an unexplained sound in a supernatural sense, but it is a physical phenomenon that challenges our current models of plasma physics. These anomalies are the most exciting part of the data. They represent the gap between what we know and what the universe is actually doing. When Voyager 1 detects a wave pattern that doesn't fit the model, it forces scientists to rethink their assumptions about the interstellar medium. The hum is not just confirming our theories, it is correcting them. It is telling us that the void is more complex, more active, and more strange than we had dared to imagine. The compressive turbulence, in particular, suggests that the magnetic fields of the galaxy are far more influential than previously thought. These fields act as a scaffolding for the plasma, guiding its flow and creating the structures that Voyager 1 is now mapping. The hum is essentially the sound of the spacecraft rubbing against this magnetic scaffolding, providing us with a tactile sense of the invisible forces that shape the Milky Way. As the probe drifts deeper, it will eventually encounter regions where the plasma density changes again. These shifts will be recorded as changes in the pitch of the hum, creating a sonic record of Voyager's progress through the galactic cloud. We are essentially listening to a long-form symphony of the void, where each movement represents a different region of interstellar space. The human reaction to this data is often one of quiet awe. The scientists who monitor the plasma wave system are not looking for loud signals or dramatic events. They are looking for the subtle shift in a frequency that indicates a new discovery. There is a meditative quality to this work, a patience that mirrors the journey of the probe itself. They are listening to the whispers of a machine that is billions of miles away, finding meaning in a hum that most people would never notice. This patient observation is what allows us to build a truthful map of the cosmos. By refusing to rush to conclusions and instead relying on the slow accumulation of plasma data, we ensure that our understanding of interstellar space is based on evidence rather than speculation. The hum is the anchor of this truth, a physical measurement that cannot be ignored or misinterpreted once the physics are understood. The interaction between Voyager 1 and the interstellar medium also teaches us about the endurance of human curiosity. We sent a machine into the dark in 1977 with no way of knowing if it would ever reach the edge of our system, let alone survive the crossing. The fact that we can still listen to the hum of plasma today is a victory of vision and engineering. It proves that we can extend our senses far beyond our biological limits, using technology to feel the vibrations of a galaxy we will never visit in person. The compressive turbulence and the density gradients are more than just data points. They are the first physical descriptions of the great outside. For all of human history, we have looked at the stars from within the bubble of the heliosphere. We have seen the light, but we have never felt the wind. Voyager 1 is the first time we have actually touched the interstellar medium, and the hum is the sensation of that touch. This tactile connection to the galaxy changes our perspective on our place in the universe. We are not just observers of a distant scene. We are participants in a larger galactic environment. The plasma waves that Voyager detects are the same waves that wash over every star and planet in the Milky Way. By listening to the hum, we are tuning into the universal frequency of our galaxy, recognizing that we are part of a vast, interconnected sea of energy. The data from the plasma wave system continues to be transmitted via the Deep Space Network. Each packet of information, a precious gift from the void. As the power levels drop and instruments are shut down one by one, the hum becomes more significant. It is one of the last remaining voices we have in the deep dark. When the plasma wave system finally fails, we will lose our only way of feeling the interstellar medium in real time. Until that day, every oscillation is a discovery. Every shift in frequency is a new piece of the puzzle. The hum of the void is a reminder that there is always more to learn, that every boundary crossed reveals a new set of mysteries, and that the silence of space is never truly silent. It is filled with the vibrations of plasma, the pull of magnetic fields, and the enduring spirit of exploration. As Voyager 1 sails on, it carries this sonic map with it, a record of the first human journey into the interstellar medium. The compressive turbulence it recorded and the density gradients it mapped will remain as the primary evidence for how our solar system interacts with its galactic neighborhood. The hum is not just a signal, it is a legacy. It is the sound of humanity stepping out of the cradle and into the vast, humming darkness of the Milky Way. To understand the true nature of this hum, we must first dismantle a common misconception about the vacuum of space. In our daily lives, sound is a mechanical wave that requires a medium, air, water, or metal, to travel from a source to our ears. Because the density of particles in interstellar space is so incredibly low, ordinary acoustic sound cannot exist there. There is no air to carry a voice, no atmosphere to vibrate with the roar of an engine. If you were floating beside Voyager 1, you would hear nothing but the internal sounds of your own suit and the rhythm of your own breath. The hum that scientists describe is not something the probe hears in the way we hear music or noise. It is a translation of plasma wave data into audible frequencies. The plasma wave system does not use a microphone. It uses an antenna to detect oscillations in the electric field caused by the movement of electrons and ions. These particles are moving at immense speeds, guided by magnetic fields, creating waves of energy that ripple through the void. When these waves hit the probe's sensors, they are recorded as voltage fluctuations over time. To make this data intuitive for human researchers, NASA scientists use a process called sonification. They take the frequency of these plasma oscillations and shift them into the range of human hearing. The resulting sound is a haunting, persistent drone, the sonic ghost of a physical reality we cannot perceive with our biological senses. This distinction is vital because it reminds us that the universe communicates in languages we were not born to understand. The hum is a mathematical representation of density and energy. When the pitch of the sonified signal rises, it indicates an increase in the local electron density. When it falls, it signals a thinning of the interstellar medium. By converting these invisible electric fields into sound, we are essentially building a prosthetic sense, allowing us to feel the texture of the void through our ears. The hum is not a noise coming from a source. It is the sound of the environment itself. As Voyager 1 continues its trajectory, these measurements allow us to define the precise limits of our solar system's influence. For eons, the sun has acted as a protective shield, blowing a constant stream of charged particles, the solar wind, outward in all directions. This creates the heliosphere, a massive bubble that deflects the majority of high-energy cosmic rays from the rest of the galaxy. The hum is our primary evidence that we have finally stepped outside this shield. By analyzing the frequency of the plasma waves, researchers can determine exactly where the solar wind ceases to be the dominant force and where the interstellar medium takes over. The data reveals a fascinating transition zone. As Voyager 1 moved toward the heliopause, it encountered a region where the solar wind slowed down abruptly, creating a pileup of particles known as the termination shock. Following this was the heliosheath, a turbulent area where the solar wind is compressed and deflected. The hum changed as the probe transitioned through these layers, reflecting the shifting pressure and density of the plasma. When Voyager 1 finally crossed the heliopause in August 2012, the nature of the signal shifted again. The plasma waves became more persistent, and their frequency stabilized at a level that matched the predicted density of the local interstellar cloud. This transition is not a sharp line like a wall, but a gradual blending of two different worlds. The hum captures this blurring effect. It shows us that the boundary between our home and the deep galaxy is porous and dynamic. There are moments when solar disturbances, massive bursts of energy from the sun, reach out across billions of miles to stimulate the plasma even in interstellar space. When these solar flares hit the edge of the heliopause, they trigger oscillations that Voyager 1 can detect as a sudden spike in the hum. This tells us that the sun is still talking to the void, and the void is responding. The implications of this are profound for our understanding of galactic weather. We often think of interstellar space as a static, empty vacuum. But Voyager's data proves it is a fluid environment. It has currents, waves, and storms. The persistent narrowband emission detected by the probe suggests that there are underlying mechanisms in the local interstellar medium that keep these plasma waves active. Some theories suggest these could be caused by the interaction of different plasma populations moving at different speeds, creating a kind of cosmic friction. Others believe it may be related to the way magnetic fields twist and snap in the void, releasing energy in bursts that ripple through the surrounding gas. By studying these patterns, we can begin to map the local fluff, the specific cloud of interstellar gas and dust that our solar system is currently passing through. We are essentially sailing a tiny boat through a vast invisible ocean, and the hum is our sonar. It tells us if we are entering a region of higher density or drifting into a cosmic cavern. This mapping is critical because the density of the interstellar medium determines how much protection the heliosphere provides to Earth. If we were to enter a significantly denser cloud of plasma, the heliopause would be pushed closer to the Sun, potentially exposing our inner planets to a higher flux of galactic cosmic rays. The hum also forces us to confront the limits of our instruments. Voyager 1 was designed in the 1970s, an era when the primary goal was to visit planets, not to spend decades in the interstellar medium. The plasma science instrument, which was intended to measure these particles directly, failed years ago during the Saturn encounter. This left scientists in a precarious position. They had the most distant observer in history, but its primary eye for plasma was blind. However, the ingenuity of the mission team allowed them to repurpose the plasma wave system, an instrument designed to detect waves rather than particles, to infer the density of the medium. This pivot represents one of the great triumphs of remote science. By observing how the plasma waves responded to solar shocks, researchers were able to calculate the electron density without needing a direct particle counter. They used the physics of wave propagation as a proxy for physical matter. This method provided the definitive proof that Voyager 1 had entered interstellar space. The frequency of those oscillations, specifically around 2.6 kHz during certain events, acted as a cosmic thermometer and barometer, confirming that the probe was no longer bathed in the solar wind. Yet, even with this success, there are gaps in our knowledge that the hum cannot fill. We can measure the density of electrons, but we cannot easily determine the composition of every ion in the interstellar medium from this distance. We know the void is humming, but we do not always know exactly what is singing. There are signals in the data that remain ambiguous, patterns of turbulence that do not perfectly align with any existing model of plasma physics. These anomalies are where the real science happens. They represent the boundary of human understanding, reminding us that for every answer Voyager provides, it uncovers three new questions. The persistence of these waves also raises questions about the energy budget of the interstellar medium. Where is the energy coming from that keeps the plasma oscillating over such vast distances? The hum suggests a reservoir of energy that is not immediately obvious. It could be the remnant heat from the Big Bang, the shock waves from ancient supernovae, or the influence of dark matter interacting with baryonic gas in ways we have yet to quantify. Voyager 1 is recording these whispers, but it lacks the sensitivity to tell us the source of every vibration. This limitation highlights the fragility of our connection to the probe. Every bit of data transmitted back to Earth must travel through a vacuum for over 22 hours before reaching the deep space network. The signal arrives as an incredibly faint whisper, barely distinguishable from the background noise of the universe. To extract the hum, engineers must use massive radio dishes and sophisticated filtering algorithms to isolate Voyager's voice from the roar of the Milky Way. It is a feat of communication that borders on the miraculous, considering the probe is running on power sources that are slowly decaying. The energy provided by the radioisotope thermoelectric generators is dwindling. To keep the mission alive, NASA has had to make agonizing choices about which instruments to keep powered. In April 2026, the low-energy charged particle instrument was shut down to conserve precious watts of electricity. This left the plasma wave system and the magnetometer as the final two science instruments capable of sensing the environment around the probe. The hum is now one of the last remaining threads connecting us to the physical reality of interstellar space. When we consider the scale of this journey, the hum takes on a more poetic significance. Voyager 1 has traveled further than any other human-made object, crossing boundaries that were once purely theoretical. It has moved beyond the reach of the solar wind and into the domain of the stars. The fact that it can still hear the plasma oscillations tells us that the universe is not an empty void, but a medium filled with invisible forces. We are learning that space is not something you travel through, but something you interact with. The compressive turbulence detected by Voyager suggests that the interstellar medium behaves more like a liquid than a gas. It can support waves, it can ripple, it can crash. This fluid nature means that the void has a geography. There are currents of plasma flowing between star systems, and there are stagnant pools of gas where particles settle for millions of years. Voyager 1 is currently navigating one of these currents, its instruments recording the friction as it slides through the galactic medium. This realization changes how we view our own solar system. We are not an island in a vacuum. We are a bubble drifting through a cosmic sea. The heliopause is the shoreline where our internal ocean meets the external tide. The hum is the sound of those two oceans colliding. By listening to this interaction, we are learning about the pressure of the interstellar medium and how it shapes the boundary of our home. This information is crucial for any future attempts to send probes even further into the galaxy. If we know the density and turbulence of the local cloud, we can better design ships that can withstand the pressures of the deep void. The data also allows us to reflect on the nature of evidence. For years, scientists debated exactly when Voyager 1 had crossed into interstellar space. The magnetic field data was suggestive, but it wasn't definitive because solar wind can sometimes mimic interstellar signatures. It was only when the plasma wave system detected the specific frequency of interstellar plasma oscillations that the debate ended. The hum provided the smoking gun. It proved that the probe was no longer in a region dominated by the sun. This transition from hypothesis to verified fact is the heartbeat of science, and it happened because a small piece of 1970s hardware continued to function billions of miles from its creators. As we analyze these signals, we are also documenting the slow death of a machine. Every transmission is a struggle against entropy. The electronics are aging, the power is fading, and the distance is increasing. Yet, the hum remains constant. There is something profoundly moving about this persistence. A lonely instrument continuing to perform its duty in a place where no human will ever go. It is a sentinel at the edge of the dark, reporting back on the vibrations of the universe until its last breath of power expires. The limits of what Voyager can tell us are now becoming apparent. It cannot see the stars it passes. It can only feel the plasma around it. It cannot map the galaxy in high resolution. It can only provide a single point of data along a linear path. But that single point is invaluable. It is the only physical measurement we have of the interstellar medium outside our bubble. Every other piece of information we have about the space between stars comes from looking through telescopes, observing light and absorption lines from thousands of light-years away. Voyager 1 is different. It is there. It is touching the plasma. The hum is the evidence of that touch. It is the physical confirmation that the theories were correct, but also a reminder that the reality is more complex than the models. The narrowband emissions and the compressive turbulence are signatures of a universe that refuses to be simple. They tell us that even in the deepest reaches of space, there is activity, energy, and change. The void is not a place of stillness. It is a place of slow, rhythmic motion. As we push the boundaries of our analysis, we find that the hum also speaks to the relationship between the local and the universal. The plasma waves Voyager detects are governed by the same laws of physics that dictate the behavior of accretion disks around black holes or the formation of planetary nebulae. By studying a few kilohertz of oscillation in our own galactic backyard, we are gaining insights into the fundamental nature of matter and energy across the entire cosmos. The data from the plasma wave system is more than just a scientific record. It is a testament to the endurance of human curiosity. We built a machine to answer a question, and decades later, that machine is still providing answers we didn't even know how to ask when it launched. The hum is the reward for that patience. It is the sound of a boundary being crossed, not just by a piece of metal and gold, but by the reach of human consciousness. We have extended our hearing into the interstellar night, and we have discovered that the night is humming with life. Not biological life, but the vibrant electric life of the cosmos itself. This sonic map will be studied for generations. Long after Voyager 1 has gone silent, the data it sent back will serve as the baseline for every future mission to the stars. We will compare the hum of the 21st century with the signals of the 23rd, tracking how our solar system moves through the galactic cloud over time. We are recording the first notes of a symphony that takes millions of years to play, and Voyager 1 is our first conductor. The persistence of the signal also reminds us of the scale of the vacuum. The probe is moving at speeds that would be unthinkable on Earth, yet it has barely scratched the surface of the interstellar medium. It is like an ant crossing a vast desert, measuring the grain of every sand dune. The hum tells us how far we have come, but it also whispers how much further there is to go. The void is nearly infinite, and our first explorer is just beginning to feel the cold wind of the galaxy. As we contemplate these final instruments, the magnetometer and the plasma wave sensor, we realize they are the only things still speaking for us in the deep dark. They are translating the invisible into the measurable, the silent into the audible. The hum is a bridge across the abyss, a way for us to feel the pulse of the galaxy from the safety of our home. It is the ultimate expression of our desire to know the unknown, to reach out and touch the void, and to find that the void has a voice. The remaining lifespan of Voyager 1 is measured in a slow, inevitable decline of voltage. Each year, the thermal generators lose a fraction of their potency, forcing engineers to prioritize the most vital functions of the spacecraft. The magnetometer and the plasma wave system are now the primary sentinels, maintaining a fragile vigil over the interstellar medium. These instruments do not see the void as we imagine it, but they feel its pressure and its magnetism. They record the subtle shifts in the galactic wind, translating the invisible plasma into data that travels across the darkness toward Earth. This process is a quiet dialogue between a dying machine and a planet that has changed entirely since the probe first left the atmosphere. The people who designed these circuits are now elderly or gone, Yet their logic still operates billions of miles away, executing commands sent from a world they no longer recognize. There is a profound stillness in knowing that Voyager 1 will eventually drift into total silence. There is no dramatic explosion or sudden failure waiting at the end of its journey, only the gradual fading of a signal until it becomes indistinguishable from the background radiation of the universe. When the power finally drops below the threshold required to operate the transmitter, the probe will not cease to exist. It will simply stop speaking. It will become a ghost ship of gold and aluminum, carrying the legacy of a species that dared to look beyond its own horizon. This transition from an active observer to a silent relic is part of the natural order of exploration. Every instrument we send into the deep eventually becomes a monument to the era that created it. The golden record remains attached to the side of the craft, a copper-plated disc protected by a jacket of aluminum and uranium. It carries the sounds of rain, the laughter of children, and the music of Bach and Beethoven. For decades, we have thought of this record as a message for others, a bottle cast into the cosmic ocean in the hope that some distant intelligence might find it. But as Voyager 1 drifts further into the interstellar hum, the record takes on a different meaning. It is no longer just a greeting to an alien world, it is a time capsule for the void itself. Even if no one ever plays those grooves, the record exists as a physical testament that we were here, that we loved, and that we wondered about the stars. The disc travels through the plasma waves, undisturbed by the vacuum, preserving a snapshot of humanity in a region of space where time seems to stretch and fold. The journey of Voyager 1 teaches us about the nature of boundaries. We spent centuries believing the solar system had a hard edge, a wall that separated our home from the rest of the galaxy. Instead, we found a gradient. We found the heliopause, a shimmering transition zone where the sun's influence fades and the interstellar medium takes hold. This boundary is not a line on a map, but a physical interaction, a place of pressure and balance. By crossing it, Voyager 1 showed us that our existence is defined by these invisible shields. The heliosphere protects us from the harshest cosmic rays, creating a sanctuary in which life could evolve and flourish. The hum detected by the probe is the sound of that shield interacting with the outside world, a reminder that we are sheltered within a bubble of solar warmth while the cold electric wind of the galaxy rushes past. As we reflect on this distance, the scale of the void begins to feel less like an emptiness and more like a presence. The interstellar medium is not nothingness. It is a thin, ionized gas, a cosmic mist that fills the gaps between the stars. It is the raw material from which new suns are born and into which old stars dissolve. Voyager 1 is swimming through this primordial soup, recording its density and its turbulence. This data tells us that we are moving through a local cloud of interstellar matter, a specific neighborhood in the Milky Way, with its own unique characteristics. We are travelers in a galactic current, drifting along with our sun toward an unknown destination. The hum is the friction of that movement, the sonic signature of our journey through the arm of the spiral galaxy. The connection between the probe and the deep space network is a thread of light stretching across the abyss. Every time a signal reaches Earth, it is a victory over distance. It is a reminder that while we are physically bound to our planet, our curiosity has no such limit. We have projected our senses far beyond the reach of our bodies, allowing us to feel the plasma of another realm without ever leaving the ground. This extension of the human spirit is what defines our place in the cosmos. We are the only part of the universe that has developed the ability to build a mirror and cast it into the dark to see what reflects back. The silence that will eventually claim Voyager 1 is not a tragedy, but a completion, The mission was designed to explore, and it has explored further than any other object in history. It has seen the rings of Saturn from angles no human eye will ever witness, and felt the transition into the interstellar void. Its purpose was not to last forever, but to push the boundary of the known just a little bit further. In doing so, it has provided a baseline of knowledge that will guide every generation of astronomers who follow. The data on plasma density and magnetic fields will be analyzed for centuries, providing clues about the structure of our galaxy long after the probe itself has become a frozen piece of debris. Now, as the cosmic journey slows in your mind, the focus shifts back from the distant void to the immediate present. The vastness of interstellar space, with its plasma hums and magnetic gradients, begins to recede into the background. The cold light of distant stars fades, replaced by the warmth and familiarity of the room around you. The scale of billions of miles shrinks down to the size of a pillow, the softness of a blanket, and the rhythmic sound of your own breathing. The universe is vast, yes, but it is also the place where you are currently resting. You are a part of that same cosmic fabric, made of the same atoms that Voyager 1 is sensing in the interstellar medium. The iron in your blood and the calcium in your bones were forged in the hearts of stars similar to the ones the probe is now drifting toward. The distance between Earth and Voyager 1 is immense, but there is a strange comfort in that gap. It reminds us that we are safe within our solar bubble, protected by the heliopause and the atmosphere of our home planet. The void is out there, humming its electric song, but you are here in the stillness of the night. The noise of the world has quieted down, leaving only the gentle pulse of existence. The worries of the day dissolve into the darkness, becoming as small and insignificant as a single grain of sand in the galactic desert. There is no need to solve the mysteries of the plasma waves tonight. There is no need to calculate the distance to the next star or wonder about the fate of a lonely probe. The journey has come full circle. We have traveled beyond the planets, past the termination shock, and through the heliopause into the deep interstellar night. We have listened to the vibrations of the void and felt the cold wind of the galaxy. But every journey requires a return. The mind drifts back from the edge of the solar system, gliding past Saturn's rings, passing Jupiter's storms, and sliding home toward the blue marble of Earth. The descent is slow and effortless, like a feather falling through a vacuum. You are returning to the place where gravity is constant and the air is warm. The darkness around you now is not the terrifying void of space, but the soft, welcoming dark of sleep. It is a space for restoration and dreams, a sanctuary where the mind can let go of its grip on reality. The hum of the universe becomes a lullaby, a distant vibration that encourages the body to relax and the thoughts to settle. The tension leaves your shoulders, your breath slows, and the boundaries of your physical self seem to blur into the quiet air of the room. You are no longer an observer of the cosmos. You are simply a part of it, resting in the cradle of a planet that spins gently through the dark. The stars continue their slow rotation above you, indifferent and eternal. Voyager 1 continues its silent glide, a tiny spark of human ingenuity moving through the interstellar mist. The two are connected by an invisible line of history and curiosity, but for now, that connection is a bridge to peace. The mysteries of the deep will still be there tomorrow. The plasma waves will still be oscillating in the void. The magnetic fields will still be shifting in the dark. There is no urgency to understand it all tonight. The world outside your window has fallen silent. The streets are empty. The lights have dimmed. and the air is cool. Inside, the atmosphere is heavy with the promise of rest. Your mind is a calm sea, reflecting the distant light of 1,000 galaxies, but the water is still. There is nothing left to seek, nothing left to find. You have traveled further than any human has ever gone, and now you have come home. The void is quiet. The probe is drifting. The signal is fading. The stars are watching. The earth is turning. The room is warm. The breath is slow. The mind is still. The journey is over. Sleep well tonight.